and today we are going with the topic is aero structures. So basically, aircraft is designed to carry some load in the air for the fast transportations, and structures are the important parts which helps an aircraft to fly without any damage to the passenger or payload or any weight. So basic function of the structure is to carry the aircraft completely without any failure or without any disturbance to the payload or to the design load. So there are basic concepts of the aircraft, like there are various structures of the aircraft. So like today's content will be like what are the design phases of an aircraft, how the aircraft is designed, like preliminary design or conceptual design, then you have detailed design. We will go through the various parts. Then there is like the structure should be integrated, like it should be uniform throughout takeoff and landing. It should not there should not be plastic deformation. Elastic deformation is not allowed. Basically, to the extent, small extent, it is allowed, which we call it a slip. That's a micro level. Then we go ahead with the major. What are the major parts in the aircraft structures, like fuselage, wing, empennage, horizontal stabilizers, um, engines. Then you come to the control surfaces to control the aircraft, to roll it, to pitch it, to nose up and nose down, like flaps, to brake for brakes, spoiler, ons, etc. We will go through the control surfaces. Then the structure, how the structure should be designed, like whether it should be monocoque or semi-monocoque. So it's like what are the advantages and disadvantages. We will go through that. Then I will show you what are the how the typical section of fuselage look like, how the wing look like, how the assembly, what are the internal structures inside the wing, or how the wing to body fuselage look like where the wing is attached to the fuselage body. We call it as central section or fuselage to body to wing joint. Then we will show you vertical stabilizers. So what are the components inside the vertical stabilizer? What are the structural components? Then what will be the loads acting on the aircraft? Like what are the stresses generated on the aircraft structures due to the load? What are the design phases, which we can tell it later, and the job opportunities and questionnaires. Okay, so now the basic thing is like preliminary design such section. Like if somebody wants to design an aircraft, like you should know what weight, what pre- preliminary important criteria one should think in the mind, like what is the distance I can carry, what is the weight I can carry, and what is the what is the life of the structure. Like if I say that okay, if the aircraft is going to fly only for 2 years, nobody is gonna buy it. If the aircraft cost is around 100 to 300 million dollars, nobody is going to. So we generally design an aircraft that should last minimum 15 years and to the period of 25 to 30 years, if provided the maintenance is done at the time and it's good enough, until and unless they don't make any catastrophic accidents. So now in the technical analysis, that is a preliminary. In the technical analysis, we think about okay, there are various loads and various things which need one should consider. So aerodynamic group is one which concentrates on like, so basically there are four governing members of an aircraft structure. One is weight of the aircraft, which for which we provide the engines to move it in the forward. We provide the engines which induces the force or thrust, we call it as, and wing provides the lift for an aircraft. And since there is a lift, and since there is an if you don't have a proper aerofoil shape, then there will be a lot of drag and it will be not efficient. That is the reason there is an aerodynamic group. In order to have in equilibrium or efficient aircraft, like wing produces the lift and engine produces the thrust. So in order to get the maximum efficiency of out of both, the aerodynamics group is so important. And then comes the structures group. Like now aerodynamic group gives you certain shape of an aircraft. So that shape should be maintained along with the strength of an aircraft. So the structures group will decide whether is it possible, is it not possible. So structure group plays very important role in testing the aircraft and all those stuff. The third is the weight and balance control group. So whenever you sit in the aircraft, always the during takeoff, nobody will allow you to lie down your seats to the back because your CG shifts, and nobody wants the CG of the aircraft while taking off. It shifts, and there are like even the cargo is loaded, and the cargo is always loaded in the center. Nobody loads the cargo in the rear or in the forward if it is an empty. If it is fully occupied, not an issue. So these are the certain groups, like power plant, which is engines group, then material and processes groups, what material and what strength allowables it can carry. So that is like the groups. These are all the groups, and the control surfaces group. Like I need spoiler, so I structures in analysis or aerodynamic analysis give you certain amount of space to fit into your control surfaces. So you should be efficient that control surfaces fit into that. But few of them are like comes into the cosmetic, and most of them major are structure analyzed by structures group. Then once you design that, okay, structure group will have two different systems, and structural systems is like interiors, which we call seats or cabin lights or thermal installation, electrical wiring on. And then come the structural groups, like what are the fuselage, wing, body, all of the control surfaces and all those. Then there is like, this is like a mandatory which is required, because nobody can think about the loads in the air. Either you have to draw it in the pen and paper, and that's why these days we use wind tunnel. Then structural labs are also there where you strength. Like for example, everybody in the engineering might have studied the tension strength. It's like pulling of the a rod, getting your tensile allowable. So for each and every component, like if it's a composite, if I have a different orientation of ply 0, 45, minus 45, 90, and with a certain set of fasteners, I test each and every configuration of an laminate to get my allowables. So you need a structural labs, you need internal labs. Then this structural test data is really important, because without allowables you cannot get margin of safety allowable by applied. Without that you won't get it, right? Then there are like propulsion for engines, like what are the vibrations coming out of engines, how the vibration will affect on the structure surrounding the engine, pylons or attachment or fan cowling or engine blades, will it come out or won't, that are done in the propulsional test. Then electronics tests, like this, I'm going to say in this era, like from 1980s or 19 early 1980s, all the aircrafts are fly by wire. Like 90%, 95% of flight is controlled by an automated software or automated tool. So only 5% time the aircraft is controlled by a pilot. So that's all the electronic tests are. So all there should be no false signal. So for example, if a hydraulic jack is not, if the landing gear is not coming down while landing, but it came down and there is no signal or no response to the cockpit, nobody can check it whether it is come down or not, until you hear the voice. So this, all the tests are done in the electronic test labs. These are various like electromechanical weapons and analog and digital computer labs, like you tabulate your configuration in the cockpits. Now this is main structures group, like which we are going to deal in future again. Like what are the structural details, like what are the importance of the structures group, or what is the aerostructure group will do it. Like once you have a conceptual design, so you model a aircraft, a small 1 as 200 or 1 as 2000, and you place it in the wind tunnel. It will only be a raw model. Like you will have wings, fuselage, basic necessary, no control surfaces. You don't deploy control surfaces in the initial phase, and you provide certain set of, since you know what will be the laid, you know your uh, weather conditions, you know your environmental conditions, you know your flight conditions, you get those flight conditions to the wind tunnel, and based on that you apply the strain gauges. You will see there are n number of strain gauges applied throughout the cross section of the fuselage, wing, stabilizers, and all those stuff surfaces. These small strain gauges will give you strains, and from the strains we get the stresses, and what's from stresses we get the loads and all those stuff. We apply the stresses. These are the raw stresses still. Now this is the one which you apply either manually in the Excel, but these days nobody uses Excel, so we do it in Nastran as a solver or Hypermesh. We apply the boundary conditions and loads in the Hypermesh. So this is the way how it is doing. Earlier till 2014, even Hypermesh was not approved for structural analysis. Before 2014 aircraft, all the models were prepared in the Patra. Now these days, the companies are okay with the Hypermesh because they were not having the certified data from the Hypermesh. Now it's like Hypermesh is like very easy rather than Pattern. Pattern is an old school, Hypermesh is a new school. So it's very easy. And we do apply the loads and create the boundary conditions, everything in Hypermesh. And then you evaluate the boundary conditions and all everything in a Hypermesh on the structural elements. You design some elements and you get the loads for that. That even we do it manually also. For example, a wing to fuselage, it's a cantilever beam. So weight of the wing, UDL, I'm going to say uniformly running load, which is stored in the tanks. Then you apply certain set of loads. You analyze it through pen and paper. I'm going to say pen and paper. We call this hand calculation is because earlier we don't used to use it. Now we do it in Excel. So it's a hand calculation. You apply your book formulas, particularly you define that wing as a cantilever beam and you analyze. Then you match your results with the Hypermesh pattern master and with your hand calculations. The result vary, but not to the extent, not beyond the extent of 10%. So that is like really important. How I'm going to say, if you have more time, you can scrutinize your Hypermesh and get the result varying from rather than 10, you can get to 5. The least expected, which we saw, was on 3%, which was done by Emra. They have really good meshing and structures team from Hypermesh and post processing group. So their results are like pretty close to the hand calculations. The deviation is only 3%. Then the structural group decides what material, what thickness, what cross sectional, all the based on your loads. Suppose if your load is too high, then the structure has to be beefy, or you have to get the stringers, stiffeners, or frames at that location. So everything will be defined by the structural analysis group. Now, the most important criteria is for a structure is to withstand the load without a failing. And next thing is it should be lightweight because it has to fly. The more the weight you put on, the more the fuel will be burned, and it won't be economical. Nobody will buy it. So the structures, like everyone will be like behind the structures team, like, okay, I don't want to increase my weight of the aircraft. Then there will be an R&D group, like in future what will be, whether we should have no joints. Like earlier we used to have a metallic aircrafts where everything will be bolted. Now if you see, the composite aircrafts are new, like whole barrel and stiffener is bonded together. There is no weld, no bolts used for I'm going to say that, not no, like drastically it has been reduced. So it's approximately 70% reduction in the bolts, and a single bolt will have a weight of around 150 to 160 grams. So if you consider a million of bolt, then it's like huge size and huge weight which is resolved. That's why these days we have shifted to the composite from the metallic, from the structures point of view. This is structural integrity, which I explained you earlier. Like what are the criteria of a structure it should have. We should know what is the stiffness it is going to. I'm going to say what are the loads it is going to carry. Based on that, you have to define the stiffness. Then what are the materials you are going to use. That based on that, you will get your allowables. And what are the stresses it is going to go through. Like if a panel is not going to go through any of the bending load, then it's not good enough to design it for bend. bending. If a panel is not going to go through any of the torsion, then nobody wants you to put on extra weight. You can reduce the weight. I mean, so you can reduce the thickness, or you can reduce the change the profile of the cross section. Then what are whether how many fasteners you need to install. There is a lot of, like, if there is a cutout, how many beefy structures around the surrounding. Like if there is a door cutout, how the structure should be behave. Like there should be very minimum load coming at the edges of free edges of the cutout. All those stuff is the structural integrity. Then you have like various like loads criteria, flight load, ground load, dynamic response, and all those stuff. These are the major. So this slide represents you major structures on the aircraft. These are all the things which are represented in this are the structures. You see, I have not shown any seats or any um any cockpit area, like so this is the radome which I was talking about earlier. It should be conical shape. So we design a structures group design. The radome should withstand 4 lb of bird strike load. So everything is like, if it is like vulture, which is like beyond 4 lb of load, then it is sure going to design it. I'm going to say fail it. But we design it based on how long or height a vulture can't fly. Not to the height of 2000 or 3000 feet, right? That's where more damage is, because that is where the speed is going to start increase. If the speed is less and the weight is more, it's not an issue. But if this even the speed is more and weight of the bird is more, then it is going to generate more loads and more damage. It's like same like a bullet fired in the water, or bullet fired in air, or bullet fired in the ice. So it's like the more resistance or more something. Then you see, this is we call it as an forward section in the Boeing methodology, or in Airbus methodology. So you see that the cockpit windows, this all are designed for burst strikes, and even for the hailstorm and all those stuff. This we call, these are various parts. I will just out the parts first, and then we can, in the next slides I will show you how the cross sections and what the loads each and everything carries. So you see in landing gears, then these are floor panels. Beneath this there will be a cargo. Beneath this there will be a seating arrangement. So this will have the bulkhead. The every panel will be shipped. To say every section will be splitted with the bulkhead. So these are bulkhead frames, which I will show you again in the next slides detail. So these are like various structures, like your engine covers, the body fairings, then pylons, then your leading edges, then your flaps, which is slitting at the back, then your ailerons, spoilers, the pylon fairings, which I said, fine call, engine call, then your main landing gear, which will be beneath this main landing gear. Then you have in the tail section, here you will have an auxiliary unit, like at the start when in the engine, because if you see, like aircraft can fly, I'm going to say aircrafts are designed to fly in the harsh condition, like minus 55 degrees Celsius to plus 55 degrees Celsius, even at some conditions plus 70 degrees Celsius. So it's like huge shift in the temperature, minus 55 to plus 70. So when whole the aircraft is like iced, then this is the engine which provides the source of um, power to whole of your aircraft. Then these are fuselage pairings. This you call it as a vertical stabilizer or radar. These are the horizontal stabilizers. These are all everything which is shown over here is the structural members. So each and everything. So in the aircraft, when somebody launch a new aircraft, 70% of the budget is spent on the aircraft structures, because it is like major portion of your aircraft. You know, I'm going to say, even you can use n number of different seating arrangements. You can ask for your own customized seats, but you can't ask for your own customized structures. No, no airline or no, you can have a modifications, but not your customized aircraft, because it will cost you in trillions or billions to run on one aircraft, single aircraft. So your seats or you lights or store head bins, those can be designed. Those are interiors part. Those are not coming into structures, and those are not designed by structure scientists. These are the control surfaces which we were talking, like spoilers or ailerons. So these are very important. Like some like spoilers are designed to, when you're hitting the ground after while landing, the aircraft speed should decrease. It can't decrease automatically. Either you have to apply the spoilers. When most of them, I think most of might you have flight in the aircraft. So whenever it is landing, the flaps spoilers are coming up and flaps are deployed down in order to increase the drag. You disturb the aerodynamic shape. That is the what basic. Then if you want to roll your aircraft sideways, you change the pitch with the elevators like this. You change the you disturb the aerodynamic flow, and that's how you get the pitching and all the stuff. These are also important, and these are also analyzed by the structural group, because these are all structures and these are required, mandatory part of an aircraft safety. These are like a, I mean to say, a front view of an aircraft, or you can call side view of an aircraft, in order to have a better, like second deck, if it is there, if it's not there, it's the same. It's all again structures.